here's a really different one from memes. Platonic solids have fascinated us for years. Do you think the exploration of four-dimensional hyperplatonic solids may be useful? So just a refresher on Platonic solids. These were known in antiquity, notably to Plato. And the question is, if you're making a solid polyhedron and you want every face to be the same, what kinds of polyhedra can you make? In 2 dimensions, if you want every analog of a face, just an edge, to be the same, you can make a polygon with any number of sides. You can make a triangle, you can make a square, you can make a pentagon, you can make a hexagon, you can make a polygon, a regular polygon, with any number of identical sides. In 3 dimensions, if you want the faces to be identical, there are only 5 ways you can do that. You can make a tetrahedron where every face is a triangle. You can make a cube where every face is a square. You can make an octahedron where there are 8 faces, they're all triangles. You can make a dodecahedron with 12 faces, each of them a pentagon. And you can make an icosahedron with 20 faces, each of them a triangle. And there are no different choices of, there are no other ways to take identical faces that are regular polygons and sort of attach them together and make them close up as an object in 3-dimensional space. So, for example, if you were to say, well, gosh, why isn't there a Platonic solid where every face is a hexagon? Well, the reason is the same reason that you can have hexagonal bathroom tilings, so to speak. When you lay out a bunch of hexagons, they just are flat. They don't curl up into a thing that makes a solid. So if you say, I really want a pentagonal, bathroom tiling, so to speak, with regular pentagons, you can't do that, because with regular pentagons, they don't lay flat like that. Instead, they sort of have to be curled up. And when they curl up, they form a dodecahedron. And so, for example, in a soccer ball, you're mixing hexagonal faces with pentagonal faces to make something that is not as closed up as a dodecahedron, but not as flat as a hexagonal tiling. So as I say, in 3 dimensions, there are exactly 5 Platonic solids. In Euclid's work on sort of proving things in geometry, turns out the theorem that takes the longest to prove, his sort of pinnacle theorem, is the theorem that there are exactly 5 Platonic solids. And he was able to prove that in antiquity, and that fact was known to Plato and so on as well. So if you go to 4 dimensions, it turns out there are a different collection of solids. There are, in that case, of regular polyhedra. They're usually called polytopes because they're just as in 3 dimensions there are faces of a polyhedron are polygons, and in a sense the faces of a polygon are the edges. Well, when you go to 4 dimensions, the faces of a polytope are polyhedra, and then the faces of the polyhedra are polygons, and so on and so on. So in 4 dimensions, they're usually called polytopes. 4 dimensions and above, they're usually called polytopes, and their faces are the lower dimensional kind of analogous regular objects. So in 4 dimensions, there are some additional kinds of regular polytopes. There's a so-called 120 cell, there's a 60 cell. A cell is the analogous word that is like the word face in 3 dimensions. A cell is kind of the 3-dimensional face of a 4-dimensional polytope. So as you look at different numbers of dimensions, there are 5 regular polytopes, which happen to be polyhedra in 3 dimensions. There are slightly more, I think, in 4 dimensions, I'm forgetting. But the most notable one is the 120 cell. It has the largest number of distinct sort of face-like things in it. Now, as you go up to higher dimensions, you'll get different numbers of regular polytopes. I think it peaks, I don't remember, maybe 8 dimensions, something like that. It peaks in some modest number of dimensions, and then when you go on going out and trying to match up all the conditions to get some regular polytope. The things that eventually that always match are the generalization of a tetrahedron and the generalization of a cube. The generalization of a tetrahedron is usually called a simplex, and you can make those in any number of dimensions. You kind of see why. Well, actually, let's do the cube because the cube is easier. Again, you can get a hypercube in any number of dimensions, and essentially what you're doing is you're going in every coordinate direction. So if you are in 4 dimensions, for example, there are 4 coordinate directions that you can move in rather than the 3 in 3 dimensions. And so you're taking all those coordinate directions, you're starting from one point and you're moving 1 unit, let's say, in each one of the directions, in each one of the, in 4 dimensions, each one of the 4 possible directions. And the things you get to by moving up to 1 unit in every direction, those are like the corners of the cube, or in the case of 4 dimensions, the 4-dimensional cube, the hypercube, often called the tesseract in 4 dimensions. And so that gives you the number of places you get to. So let's see, in the case of a square, there are 4 corners of a square. In the case of a cube, there are 8 corners of a cube, and in the case of a tesseract, a 4-dimensional cube, you're going along each. Let me think. That would be it should be 2 to the n. Am I getting this wrong? It's 2. It's 4. It's 8. Yes, it's 2 to the n. It's for every time you add a dimension, you're multiplying by 2 the number of corners that the object has. So in the tesseract then has 16 corners, so to speak, and you're filling it in like a cube. And that you can keep on doing that in any number of dimensions. You get an object that is a hypercube. You can also get a simplex by instead of filling out sort of instead of allowing yourself to go. So in a cube, for example, the corners of a cube have coordinates that are things like 0, 1, 0 or 1, 0, 0. All combinations of 1s and 0s of length, well, n if you're in n dimensions, all combinations of sequences of 1s and 0s are possible coordinate positions for the corners of a hypercube. So there are 2 to the n of those because each position is either 0 or 1, and there are n positions, so there's 2 to the n possibilities. In the case of a simplex, you're doing the same thing, but you're only having 1, 1 there. And the others, is that right? Is it 1, 1, 2 1s? Anyway, it's a limited number of 1s. And that gives you these kind of slanted faces. You don't get to sort of have the diagonal corner of the cube. So, any case, those exist. The dual of a tetrahedron, which is an octahedron in 3D, the analog of that exists in any number of dimensions. So does one care about these higher dimensional objects, these higher dimensional polytopes? There are a number of applications for these things. Sometimes they're useful as a way to kind of define how you kind of can move data around in an optimal fashion. They're kind of switching networks that are based on these kinds of things. They're also, they have, that's one use. I don't know of too many. I mean, that's the most common, that's the one that most comes to mind for me. In mathematics, there are a bunch of uses to do with understanding group theory and so on that show up. And you can also ask questions like, well, here's an example of a question. How well can you approximate a sphere or a hypersphere by a polytope, by a regular polytope, a polytope where all the faces are the same? So in 2 dimensions, you've got, a triangle, a square, a pentagon, a heptagon, a hexagon, a heptagon, etc. By the time you've got, a 1,000-sided regular polygon, you've got a pretty good approximation to a circle. So in 2 dimensions, pretty easy to approximate a circle, but with a polygon. In 3 dimensions, the best you're going to get to approximate a sphere is an icosahedron or a dodecahedron, depending on how you're doing the approximation. You don't get to make to make a sort of soccer ball that more closely approximates a sphere. You have to make something that isn't like a regular polytope. You have to have something where you're mixing pentagonal faces and hexagonal faces in that case. So it's an interesting question how well you can approximate a sphere with polytopes in different numbers of dimensions, and that's kind of an interesting issue because that then relates to it relates to a variety of things about it relates to some things about error correcting codes, and it also relates to things where you're making discrete approximations to kind of continuous systems where you can rotate in any direction. When you make a discrete approximation, you need something where you can just have elements, for example, on the corners of a regular polytope. Maybe I'll explain that comment about error correcting codes. So we're a little bit off the future question, but maybe I'll explain something about error correcting codes anyway. So the issue is you are trying to send a message and you're sending a sequence of numbers, let's say 7, 5, 8, 2, 4, 6, whatever. And let's say you represent those numbers. Let's say you're representing numbers from 0 to 7. You can do that with 3 binary bits. 0, 0, 0 for 0, and then 0, 0, 1, et cetera, up to 1, 1, 1, which is the binary for 7. Okay, so if all you're doing is to send those bits, then anytime there's a bit that's wrong, if, for example, you thought you were sending 1, 0, 0, but actually you sent 1, 0, 1, you thought you were sending a 4, but actually you'll get a 5. So if you're just sending the raw bits, anytime there's a single bit error, there's a mistake that's been made. Well, there's this concept of error correcting codes, where what you do is to, let's say, add a bit. And then what can happen is that that gives you sort of more redundancy. And then you can say, well, if I get either this sequence of bits or that sequence of bits, then I know that really means a 4. And so you're using a certain number of extra bits to represent kind of error correction. Now, the way error correction is usually done, instead of correcting every single number you're sending over, you're correcting blocks of numbers, and you're sort of adding some error correction to that whole block of numbers, and you're adding error correction that can correct, let's say, up to a 1-bit error in this whole collection of numbers. And so that's kind of the approach to doing error correction. And you see error correction, for example, if you look at the ISBN numbers on books, there'll be a 1-2752 dash blah 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 dash blah blah blah. In that case, the last digit is a check digit, I guess, which is sort of the junior version of error correction, is just to know that there was a mistake. It turns out the mathematics of these things works much better when the base of the numbers is a prime. And so that's why in ISBN numbers, you'll sometimes see an X there as well as all the numbers, because it's being done in base 11, because 11 is a prime, and the X represents the digit 10 in base 11. So in any case, error correcting codes. So there are all kinds of different schemes for making error correcting codes, all kinds of different ways that you can add those extra bits to be able to detect errors, be able to correct errors, and so on. Well, turns out a way to think about what's going on is in terms of spheres in high-dimensional space. So the way to think about it is, if you've got some sequence, 1, 0, 1, 1, 1, whatever, you can think about that as a coordinate position if you've got n digits, you can think about that as a coordinate position in n-dimensional space. And every one of those, you're kind of asking that every possible thing you might send is a position in n-dimensional space. So So you've got all these different things, 1, 0, 0, 1, 0, 1, all that kind of thing. They're all positions in n-dimensional space. And if you make a 1-bit change, it's like moving a certain, if you make any one of the possible 1-bit changes, it's kind of like moving a certain direction, but you don't know what the direction is. And if you're moving a certain amount in some direction, but you don't, but it's sort of equal what happens in all directions, it's like having a sphere in n-dimensional space. So the kind of the problem of error-correcting codes ends up being, how do you arrange the kind of code words, the ways you represent these different things you're trying to send? How do you represent those so that if you make a 1-bit change, you're least likely to interfere with another code word, with a code word that's representing a different number, let's say. And so that problem becomes a problem of sphere packing in high-dimensional space, because each sort of every code word is a point in high-dimensional in your n-dimensional space, and the error, sort of a 1-bit error, for example, corresponds to a sphere around that point. That what's in that sphere are sequences that you can reach by making a 1-bit error from the original code word you had. So the problem of error correction, of finding error correcting codes, if you want a length n error correcting code, you're dealing with essentially sphere packing in n-dimensional space. And turns out that there's all kinds of cool things that happen with sphere packing in n-dimensional space. And there are certain dimensions, like 26, for example, where it turns out to be possible to have this kind of lattice where you pack spheres in this kind of regular array, hyperspheres in this regular array, and they pack really, really well. In 2 dimensions, when you're packing circles, the best packing is a hexagonal packing, where you're just sort of making where the arrangement of the centers of the circles, if you get a bunch of coins, you just smoosh them together, they'll form this, if they're the same size coins, they'll form this kind of hexagonal array. And that's the closest packing in 2 dimensions. In 3 dimensions, it was guessed by Kepler that the closest packing is the one you often see in grocery stores, where you kind of have this packing of spheres, spherical fruit is typically packed that way. Let's see, in that case, so in 2 dimensions, the number of neighbors of a circle that's optimally packed is 6. In 3 dimensions, the number of neighbors is 12, I think, for the optimal packing. And the sort of in 2 dimensions, the optimal shape is a yeah, this is tricky, but the optimal shape, the sort of region around every circle is a hexagon. In 3 dimensions, I think it's a tetrachedecadon, which is a 14. Is that right? Which is a 14-faced object. And that's a tricky thing because there's this thing, it's called the kissing number, which is the number of points where the spheres actually touch, where the and that's a different number than the size of the number of faces in the polytope that encloses each sphere. But roughly, there's in 3 dimensions, only proved about 20 years ago now that packing, sort of the regular packing that you see with fruit in grocery stores and so on, is in fact the best packing that you can get in 3 dimensions. But when you go to higher dimensions, some dimensions it's known what the closest packing is, some it isn't. There's some dimensions where, for weird reasons of the way that numbers line up and so on, you end up with these very dense packings, very good ways to pack things, but only in that number of dimensions. And so those are cases where you can get good error correcting codes where the code words are like length 26, for example. And there's sort of a close relation between the mathematics of those kinds of codes, the mathematics of finite groups, the mathematics of sphere packing, and so on. These are all very related kinds of things. So I think the question was, are there applications of higher dimensional kind of polytopes, regular polytopes? And so I'm sort of giving you a first approximation to that. I think these optimal lattices don't involve regular polytopes. I think they involve different shapes, as I think they even do in 3 dimensions. So it's related, but not quite the same thing.